Everything you thought you knew about Artemis 3 is wrong. Not partially wrong, not slightly off. Fundamentally, structurally, cosmically wrong. In ways that will reframe everything you believe about what humanity is actually about to do on the surface of the moon. You were told it was a return, a triumphant homecoming. Astronauts planting boots where Apollo left footprints, carrying the weight of a half-century of waiting back to the gray dust of the lunar surface. That was the story. That was the headline. That was the version sold to the public in press releases and agency briefings and carefully edited mission animations. But the moon that Artemis 3 is targeting is not the moon of Apollo. It is not the pale, familiar satellite that hung over the shoulders of Armstrong and Aldrin. The landing zone chosen for this mission sits at the South Pole, a region of the moon that no human being has ever stood upon, a region that operates under entirely different physical laws than anything the original lunar program ever encountered. At the lunar South Pole, the sun never rises high. It drags itself along the horizon in a permanent shallow arc, casting shadows that have not moved in billions of years. Not millions, billions. There are craters at those coordinates where sunlight has been absent since before the Earth had oceans, since before life existed anywhere on this planet. The darkness in those craters is not the darkness of a cloudy night or a power outage. It is the darkness of geological time. Cold, ancient, absolute. And inside that darkness, something has been waiting. Water ice, trapped in the regolith, locked beneath the surface at temperatures colder than the surface of Pluto. Hundreds of millions of tons of it, possibly more, accumulated over eons as comets and asteroids delivered their frozen payloads to a place cold enough to hold them forever. Artemis 3 is not going back to the moon. It is going somewhere no human being has ever been, to extract something that will determine whether our species ever leaves this solar system. The stakes are not national pride. They are not scientific curiosity. The stakes are the entire future trajectory of human civilization, compressed into a single mission, targeting a crater rim at the bottom of the world, where the sun barely breathes, and the shadows remember the beginning of time. This is not the mission they told you about. This is something much larger, much stranger, and far more dangerous than any press release will ever admit. To understand what Artemis 3 is truly attempting, you must first understand the nature of the place it is going, not as a coordinate on a map, not as a set of latitude and longitude numbers transmitted between mission computers. You must understand it the way a geologist understands a canyon, by feeling the weight of everything that happened there before you arrived. The lunar South Pole is one of the most extreme environments in the known solar system. That statement is not hyperbole. It is a physical fact that emerges directly from the geometry of the moon itself. The moon's axial tilt is only about 1.5 degrees. 1.5 degrees. Compare that to Earth's 23.5 degree tilt. The tilt responsible for our seasons, our long summer evenings, the way the light changes in October and makes everything feel like an ending. The moon has almost none of that. It barely nods toward the sun at all. The consequence of that near-perfect uprightness is staggering. At the lunar South Pole, the sun never climbs above a few degrees above the horizon. It skims, it grazes, it moves in a slow, eternal circle around the edge of the sky, never rising, never setting in any meaningful sense, casting light that arrives almost horizontally. The way sunlight arrives on Earth only at the very edge of a winter sunrise, stretched thin and long across a frozen field. Now imagine that geometry applied not for a morning, not for a season, but for 4.5 billion years. The craters at the lunar South Pole, Shackleton, Hayworth, Noble, de Gerlach, are deep enough and positioned at precisely the right angle that the sunlight grazing the pole never reaches their floors. The crater walls block it, have always blocked it, will always block it, for as long as the moon exists and the sun burns. These are not places that are currently in shadow because of some temporary alignment. These are places that are structurally, permanently, cosmically excluded from sunlight by the shape of the terrain itself. Scientists call them permanently shadowed regions. The name is accurate, but it is also the most profound understatement in all of planetary science. Think about what permanent means on a geological timescale. The last common ancestor shared by humans and chimpanzees walked the Earth approximately 6 million years ago. The age of those shadows is roughly 750 times older than that moment. When the first multicellular life was learning to organize itself in Earth's shallow seas, those crater floors were already ancient dark. When the dinosaurs rose and fell across 160 million years of dominance, those shadows did not move. Not a centimeter. Not a photon of direct sunlight touched those floors during the entire Mesozoic era. That kind of permanence does something to a place. It is not merely absence of light. It is the accumulation of absence. A cold so deep and so sustained that it becomes geological in its own right. The temperatures inside these craters drop to approximately -230 degrees Celsius. That is colder than the surface of Neptune, colder than the upper atmosphere of Pluto. At those temperatures, chemical reactions that would take microseconds elsewhere slow to timescales that make geology look impatient. Molecules lock into place and stay. Nothing evaporates, nothing migrates, nothing changes. These craters are not just dark, they are frozen in time. And here is where the philosophy of the place reveals itself with a clarity that is almost unbearable. Everything that entered those craters, every atom, every molecule, every fragment of ice delivered by every comet and asteroid that impacted the lunar surface over 4 billion years, is still there, still exactly there, unchanged, unaltered, preserved at the molecular level, with a fidelity that no laboratory on Earth could replicate. The water ice sitting inside Shackleton Crater did not form on the moon. The moon is geologically dry. Its violent formation in a catastrophic collision between the proto-Earth and a Mars-sized body called Theia vaporized virtually all volatile compounds, including water, in temperatures so extreme that rock itself became gas. The water at the South Pole arrived from elsewhere. It rode inside comets, those ancient dirty snowballs that formed in the outer solar system billions of years ago, and inside carbonaceous asteroids, the dark, carbon-rich remnants of the early solar system's chemistry. Each impact delivered its payload of ice, and the ice migrated, molecule by molecule, hopping across the lunar surface in the weak sunlight until it reached the cold traps of the permanently shadowed regions where it stopped forever. Some of that ice is ancient beyond reckoning. Some of it formed in the molecular clouds that existed before the sun was born. Ice that predates our entire solar system, that carries within its crystalline structure the chemical signature of the universe as it existed 5 billion years ago. To stand on the floor of Shackleton Crater and hold a handful of that regolith would be to hold something older than the Earth itself. Older than the moon. Ice that was already billions of years old when our sun ignited for the first time. The astronauts of Artemis 3 will not land on the crater floor itself. The engineering challenges of that descent remain prohibitive for this first mission. They will land on the rim, in the regions of near-permanent sunlight that sit just above the eternal dark. The crater rim at the South Pole experiences something almost paradoxical. While the floor below is in perpetual night, the peaks of the rim can receive sunlight for up to 90% of the lunar year, making them simultaneously the brightest and the darkest places on the moon within a few kilometers of each other. This contrast, the razor-thin boundary between perpetual light and perpetual shadow, is one of the most violent environmental gradients anywhere in the inner solar system. Step from the illuminated rim into the shadowed crater, and within meters, the temperature drops by more than 300 degrees. 300 degrees. The thermal shock alone would destroy most unprotected materials instantly. The suits that Artemis astronauts will wear, the XEMU, the Axiom Space Extravehicular suits, are engineered specifically to survive this transition, insulated against a thermal environment that exists nowhere else in human spaceflight history. But the physical danger is only part of the story. The deeper challenge is navigational and psychological. Inside the permanently shadowed regions, there is no light. Not dim light. Not reflected earthshine. True darkness, the kind of darkness that the human visual system cannot adapt to, cannot function within, cannot overcome. The astronauts will navigate by instruments, by helmet-mounted lights that illuminate perhaps 10 meters ahead, by sensor packages and ground-penetrating radar. They will move through one of the most scientifically valuable environments in the solar system, while being essentially blind in it. There is a philosophical weight to that image that demands acknowledgement. The most precisely trained human beings in the history of our species, wearing the most sophisticated life support technology ever constructed, carrying instruments of extraordinary sensitivity, and they will still be unable to simply look around and understand where they are. The darkness is too complete, too ancient, too absolute to be overcome by any light we can carry. Humanity has always used light as its primary metaphor for knowledge. We speak of enlightenment, of illumination, of bringing things to light. We describe ignorance as darkness. And here, at the most scientifically critical location we have ever chosen to visit, the darkness is not a metaphor. It is a physical reality that cannot be dispelled. It can only be navigated, slowly, carefully, instrument by instrument, step by careful step. That is not a failure of our technology. That is a lesson from the cosmos. There are places where the instruments must speak because the eyes cannot. There are truths that cannot be seen directly, only inferred, measured, modeled, deduced from signals and data rather than from sight. The lunar South Pole is a physical demonstration of an epistemological reality that applies far beyond space exploration. Some of the most important things in the universe are hidden in the dark, and the only way to find them is to stop waiting for the light and start trusting the instruments. Artemis 3 is going to a place that the sun forgot, a place that time itself seems to have passed over. And what it finds there, in the ice, in the ancient chemistry of comets and asteroids frozen into the regolith, will not just answer questions about the moon. It will answer questions about the origin of water on Earth, about whether the building blocks of life arrived here on the back of the same comets that seeded the lunar cold traps, about whether the ice at the South Pole carries organic molecules, amino acids, complex carbon compounds that were present in the solar system before any planet had formed. The moon's South Pole is not a destination. It is an archive. The oldest, coldest, most perfectly preserved archive in the inner solar system. And Artemis 3 is about to open it for the first time. What it finds inside may change everything. Water is so ordinary on Earth that we have made it invisible. It falls from the sky. It fills the oceans. It runs through pipes in the walls of every building humanity has ever constructed. Children play in it. Civilizations are built along its edges. We drink it without thinking, bathe in it without wonder, watch it evaporate from a cup of coffee, and think nothing of the miracle occurring in front of our eyes. But water is not ordinary. Water is extraordinary in ways so deep and so strange that planetary scientists still argue about its origins, still debate the exact chain of events that brought it here, still find new surprises in the chemistry of a molecule so familiar that most people could not tell you why it matters that it bends at an angle of 104.5 degrees between its two hydrogen atoms. That angle is not a trivial detail. That specific geometry, the precise shape of the water molecule, the way its oxygen atom pulls electrons toward itself and creates regions of positive and negative charge on a molecule so small it is invisible to any conventional microscope, is what gives water its extraordinary properties. Its unusually high boiling point, its ability to dissolve more substances than almost any other liquid. The fact that its solid form floats on its liquid form, which is almost unique among compounds, and which means that when lakes and oceans freeze, they freeze from the top down, preserving liquid water beneath the ice where life can continue to exist through winter. If water froze from the bottom up, as most substances do, the oceans would have frozen solid billions of years ago. Life as we know it would never have survived the first major ice age. The angle of a single molecule, 104.5 degrees, may be one of the reasons you exist. And that molecule, that precise geometric miracle, is what sits frozen in the darkness of the lunar South Pole. Hundreds of millions of tons of it, possibly billions of tons, locked in the regolith at temperatures where it will remain stable for geological eternities unless something disturbs it. But where did it come from? That question is not as simple as it sounds, and the answer reaches back to the very beginning of the solar system, to a time before the sun had stabilized its fusion reactions, before the planets had finished forming, before the distinction between inner solar system and outer solar system had fully established itself. In the first few million years after the sun ignited, the solar system was a violent, chaotic place. The region close to the young star was too hot for volatile compounds. Water, carbon dioxide, ammonia, methane, to condense into solid form. Everything within a certain distance from the sun, a boundary that planetary scientists call the frost line or the snow line, existed only as gas. Beyond that line, in the cold outer reaches of the early solar system, volatiles could freeze. They did freeze. They accumulated on the surfaces of dust grains, building the icy bodies that would eventually become comets and carbonaceous asteroids. The Earth formed inside the frost line, in the hot inner solar system, assembled from rock and metal. It formed dry. The geological evidence is unambiguous. The early Earth, in the first hundreds of millions of years of its existence, had far less surface water than it does today. The oceans, the rivers, the groundwater, the atmospheric moisture that drives our weather. All of that water had to arrive from somewhere. The leading hypothesis, supported by isotopic analysis of ancient zircon crystals and the chemical signatures of primitive meteorites, is that much of Earth's water arrived from the outer solar system. Comets delivered some of it. Carbonaceous chondrite asteroids, the dark, carbon-rich, water-bearing rocks that formed beyond the frost line and were later scattered inward by gravitational interactions with the giant planets, delivered more. Over hundreds of millions of years, during a period of intense bombardment called the Late Heavy Bombardment, the inner solar system was pelted with material from the outer reaches, and that material brought water. The same process that watered the Earth also seeded the Moon. The Moon, being smaller and lacking a strong gravitational field to retain an atmosphere, could not hold water on its sunlit surface. The water that arrived there evaporated, dissociated under ultraviolet radiation, and was lost to space except for the fraction that migrated into the cold traps. The fraction that found its way to the permanently shadowed craters at the poles and stayed. That water is therefore a sample of the same reservoir that gave Earth its oceans. It carries the same isotopic signatures, the same chemical history. If the ice at the lunar South Pole contains deuterium, the heavy isotope of hydrogen, in ratios that match the water in Earth's oceans, it would be powerful evidence that cometary and asteroidal delivery was the dominant mechanism for Earth's water. If the ratios are different, it raises new questions about where exactly Earth's water came from, and whether the story is more complicated than current models suggest. This is science of the most profound kind. Not science that answers technical questions for a narrow audience of specialists. Science that answers questions every human being has implicitly asked without knowing they were asking it. When you drink a glass of water, where did that water come from? The answer involves comets. It involves asteroids. It involves the chaotic dynamics of a young solar system 4.5 billion years ago. It involves the geometry of a molecule bent at 104.5 degrees and the cold, dark floors of craters on a world 280,000 miles away. Artemis 3 will drill into that ice. We'll extract it. We'll analyze its isotopic composition with instruments sensitive enough to distinguish between hydrogen and deuterium at concentrations of parts per million. And the data those instruments return will be, in a very literal sense, the biography of Earth's oceans, written in the ice of another world. But the water is only the beginning of what the lunar South Pole holds. Because wherever water exists in the cosmos, chemistry follows. Organic chemistry, the chemistry of carbon compounds, of molecules with backbones of carbon atoms linked in chains and rings and spirals. The molecular architecture from which life is built. The permanently shadowed regions are not simply cold traps for water. They are cold traps for everything. Every volatile compound that arrived at the lunar surface over billions of years and migrated to the poles is potentially preserved there. Comets are not made of pure water ice. They are complex chemical mixtures. Water, carbon monoxide, carbon dioxide, methane, ammonia, hydrogen cyanide, formaldehyde, and dozens of more complex organic molecules. Carbonaceous asteroids carry amino acids, the molecular building blocks of proteins, the structural units from which all known life constructs its fundamental machinery. Amino acids have been found in meteorites recovered on Earth. The Murchison meteorite, which fell in Australia in 1969, contained over 90 different amino acids, far more than the 20 used by life on Earth, including several that are not used by any known biological system. These molecules formed through purely chemical processes in the cold, radiation-bathed environment of the early solar system, without any biological catalyst, without any living system to guide their assembly. Chemistry alone, given the right ingredients and enough time, builds the molecules of life spontaneously. If those same molecules are preserved in the lunar cold traps, if the ice at the South Pole is laced with amino acids, with nucleobases, with complex organic compounds, then the moon holds something even more extraordinary than water. It holds a frozen sample of the prebiotic chemistry of the early solar system. The raw ingredients, the molecular starter kit that may have been delivered to Earth and that, under the right conditions, organized itself into the first self-replicating structures, the first primitive metabolism, the first flickering of what we would eventually call life. Standing at the edge of Shackleton Crater, looking down into a darkness that predates multicellular life on Earth, an Artemis astronaut would be standing at the boundary between two worlds: the warm, lit, living world of the present and the cold, dark, preserved world of the deep past. The crater rim is a temporal threshold. Above it, the present. Below it, 4 billion years of unchanged chemistry waiting to be read. There is a word in geology, unconformity, that describes a boundary in rock strata where two very different periods of geological time meet, where a long gap in the record exists, where erosion or absence of deposition created a missing chapter, and then deposition resumed. When you see an unconformity in a cliff face, you are looking at time itself rendered visible. The place where the record jumps, where millions or hundreds of millions of years are compressed into a single surface. The rim of a permanently shadowed crater at the lunar south pole is an unconformity in the history of the solar system. Above it, the accumulated record of the last 4 billion years, cratered, gardened by micrometeorite impacts, churned by the slow processes of space weathering. Below it, something close to the original chemistry, something that bypassed the churning, something that was sealed into cold storage before most of the geological history we know had even begun. Reading that record will require extraordinary care. The instruments on Artemis 3 are designed to minimize contamination, to preserve the integrity of samples taken from the shadowed regions, to analyze ice in place before it ever reaches the warm interior of a sample container where sublimation could alter its composition. The science is meticulous, painstaking, slow, the exact opposite of the thunderous spectacle of launch and landing that draws the public's attention. But that slow, meticulous science is where the real story lives. Not in the fire of the SLS rocket or the drama of the lunar landing. In the quiet, precise moment when a drill penetrates frozen regolith that has not been disturbed since before the Cambrian explosion, and a sensor reads the chemical signature of a molecule that has been waiting in the dark for 4 billion years for something with the curiosity to find it. The universe does not volunteer its secrets. It does not arrange them conveniently at eye level, in the light, where they are easy to reach. It buries them in the coldest, darkest, most inaccessible places it can find. And then it waits, with the infinite patience of deep time, to see which species eventually develops both the technology and the will to go looking. For 4.5 billion years, the ice at the lunar South Pole has been waiting. Artemis 3 is the answer. There is a certain arrogance embedded in the act of sending a human being to the moon. Not the arrogance of pride or ego, though those forces are certainly present in any space program. A deeper arrogance, a biological arrogance, the arrogance of a creature that evolved over millions of years in the warm, oxygen-rich, magnetically shielded, gravitationally stable environment of a living planet, and decided to take that body, with all its fragility and all its evolutionary baggage, into an environment so hostile that every single parameter of the cosmos seems calibrated specifically to destroy it. The human body is a machine built for Earth. Every system, every organ, every molecular process operating inside you right now was selected by billions of years of evolution to function within a very narrow range of conditions. Temperature between roughly 36 and 38 degrees Celsius at the core. Atmospheric pressure near 1 bar. Oxygen concentration near 21%. Gravity at approximately 9.8 meters per second squared. Electromagnetic radiation filtered by a magnetic field and an ozone layer that together block the wavelengths most destructive to biological molecules. Remove any one of those parameters, and the machine begins to fail. Remove several simultaneously, and it fails catastrophically in minutes. The environment of the lunar South Pole removes all of them at once. Begin with temperature. The human body loses heat continuously to its surroundings through radiation, conduction, and convection. In an environment at negative 230 degrees Celsius, the thermal gradient between a living human body and the surrounding environment is approximately 268 degrees. Heat flows from warm to cold, with an urgency proportional to that difference, without the insulating layers of the extravehicular suit. Multiple shells of advanced materials, each designed to trap radiated heat and block the flow of thermal energy outward. A human being on the floor of a permanently shadowed crater would lose body heat so rapidly that core temperature would become incompatible with consciousness within seconds and incompatible with life within minutes. The suit is not merely clothing. It is an entire artificial environment, a miniature Earth carried around the body, recreating within its sealed interior the precise conditions under which human physiology can function. It maintains temperature. It supplies oxygen at the correct pressure. It removes carbon dioxide before it accumulates to toxic concentrations. It regulates humidity. It provides a mechanical counterpressure against the vacuum outside that would otherwise cause the tissues of the body to swell, the dissolved gases in the blood to come out of solution in a process similar to decompression sickness, the moisture on the surface of the eyes and lungs to begin evaporating directly into space. The vacuum of space is not merely the absence of air. It is a thermodynamic and biological assault on every surface it contacts. The soft tissues of the human body, the mucous membranes, the alveoli of the lungs, the corneas of the eyes, are designed to exist in contact with gas at specific pressures. Remove that gas, and those surfaces are exposed to conditions so far outside their operational parameters that the cellular damage is immediate and irreversible. But temperature and vacuum, as extreme as they are not the most insidious threats at the lunar South Pole. The most insidious threat is invisible. It arrives without warning, without sensation, without any biological signal that something dangerous is happening. It accumulates silently inside the cells of the body, breaking molecular bonds, fragmenting DNA strands, disrupting the precise chemical signaling that allows cells to function and divide and repair themselves. It is radiation. The Earth is wrapped in 2 protective layers that most people never think about. The first is the magnetic field, generated by convection currents in the liquid iron outer core of the planet, extending tens of thousands of kilometers into space, deflecting the charged particles of the solar wind around the planet like water flowing around a stone. The second is the atmosphere, a column of gas 10 kilometers deep that absorbs and scatters the high-energy photons and secondary particles that the magnetic field does not catch. The moon has neither. The moon's magnetic field is a ghost, a remnant of an ancient field that died billions of years ago when its core cooled and solidified, leaving behind only localized crustal magnetism too weak and too patchy to provide any meaningful protection. The moon's atmosphere is so thin, it is technically classified as an exosphere. a sparse collection of atoms liberated from the surface by solar radiation and micrometeorite impacts, present in concentrations so low that the average distance between molecules is measured in kilometers rather than nanometers. It provides zero radiation shielding. An astronaut standing on the lunar surface is exposed to the full spectrum of space radiation. The galactic cosmic rays, high-energy particles accelerated by distant supernova explosions, traveling at significant fractions of the speed of light, carrying energy so extreme that they punch through centimeters of aluminum shielding as if it were not there. The solar energetic particles, bursts of protons and electrons ejected by solar flares and coronal mass ejections, arriving at the moon with little warning and in doses that can reach dangerous levels within hours. The constant background flux of solar wind protons, lower in energy but continuous and cumulative. Current radiation models estimate that an astronaut on a lunar surface mission receives a radiation dose roughly 200 times higher than a person living on Earth's surface. Over a mission duration of 6 to 8 days. The planned duration for Artemis 3 surface operations. The accumulated dose remains within acceptable career limits as defined by current spaceflight medical standards. But those standards themselves represent a compromise between mission objectives and acceptable risk. They are not zero risk. They are a calculated trade, a decision made by human beings in conference rooms on Earth that a certain probability of elevated cancer risk, years or decades in the future, is an acceptable cost for what the mission will achieve. Every Artemis astronaut who sets foot on the lunar surface is making that trade with full knowledge of what it costs. That is not a trivial observation. It is one of the most profound ethical and personal dimensions of human spaceflight. The willingness to accept biological damage, to allow the cosmos to reach inside the body and leave its mark at the molecular level, in exchange for the knowledge and experience and progress that the mission provides. There is something philosophically significant about the fact that we cannot send our minds to the moon without also sending our bodies. We cannot dispatch a purely intellectual presence, a disembodied curiosity, to stand at the rim of Shackleton Crater and observe. We must send the entire biological package, the fragile, warm, radiation-sensitive, thermally vulnerable, oxygen-dependent machine that evolution built for a completely different environment. And that machine must be kept alive every second of the mission by a technological infrastructure of extraordinary complexity and redundancy. The extravehicular suit alone contains over 300 individual components. Its life support backpack, the primary life support system, circulates oxygen, scrubs carbon dioxide using lithium hydroxide canisters, regulates pressure, manages thermal output, and monitors the health of the astronaut inside through a suite of biosensors that transmit data continuously to mission control. The suit is not passive protection. It is an active, dynamic system, constantly adjusting, constantly compensating, constantly maintaining the narrow band of conditions inside which a human being can remain alive and functional. And even with all of that technology, the margin is not comfortable. The lunar South Pole introduces failure modes that no previous spaceflight mission has faced. The extreme cold of the shadowed regions can affect suit materials in ways that warm lunar surface operations never required testing for. Lubricants used in suit joints can thicken or fail at temperatures approaching -200 degrees. Seals can become brittle. Sensors calibrated for warmer environments may read incorrectly. The dust, the lunar regolith, is itself a serious engineering hazard, with particles so fine and so electrostatically charged that they adhere to every surface they contact. Clogging seals, abrading visors, potentially compromising the integrity of systems that depend on tight tolerances. Lunar dust is unlike any dust on Earth. On Earth, dust particles are rounded by the action of wind and water, the same weathering processes that smooth river stones and erode cliffs. The Moon has no wind, no water. The regolith has been shaped exclusively by micrometeorite impacts and the thermal cycling of the lunar day-night cycle over billions of years. And the result is particles with sharp, jagged, glassy edges. Tiny shards of pulverized rock and glass that cut into surfaces at the microscopic level. The Apollo astronauts returned with suits visibly degraded by just a few hours of surface operations. Artemis astronauts will spend far longer on the surface, in a region where the dust has never been disturbed by any human activity, where its abrasive properties remain fully intact. Every one of these challenges was known before the mission was designed. Every one of them has been engineered around, tested for, modeled, simulated, rehearsed in vacuum chambers in cold environments and analog sites in Antarctica and the high desert. The engineering response to the hostility of the lunar South Pole represents one of the greatest sustained technical efforts in human history. Years of work by thousands of people, measured in billions of dollars and millions of person-hours, all directed at the single problem of keeping two human beings alive in an environment that every physical law of the cosmos conspires to make lethal. And yet, in the context of the universe, this extraordinary effort is also deeply humbling. Because the Moon is not a particularly hostile environment by cosmic standards, it is, in fact, one of the most accessible extraterrestrial surfaces in the solar system. Geologically quiet, without a crushing atmosphere or intense magnetic field interactions, at a distance that allows communication with a delay measured in seconds rather than minutes or hours. If keeping two humans alive on the Moon for a week requires this level of engineering complexity, this level of cost and risk and preparation, then the challenges of sending humans to Mars, where the distance is hundreds of times greater, the mission duration is years rather than days. The radiation exposure is dramatically higher, and the return option in an emergency is essentially non-existent. Are not merely more difficult, they are categorically different in kind. Artemis 3 is not just a mission to the Moon. It is a test of the outer limit of what current human spaceflight technology can sustain. It is the frontier, the absolute edge of where the life support envelope can be stretched while still maintaining an acceptable margin of safety for human life. Everything beyond it, the asteroids, Mars, the moons of Jupiter and Saturn, lies outside that envelope as it currently exists. To reach those destinations, the envelope must be fundamentally redesigned. New materials, new radiation shielding, new life support architectures, new medical capabilities for diagnosis and treatment without access to Earth-based hospitals. The body that evolution gave us was not built for the cosmos. But we are taking it there anyway. We are taking a creature of warm oceans and breathable air and stable gravity into the hardest vacuum, the deepest cold, the most radiation-drenched surfaces in the inner solar system. And we are doing it not because it is easy. That phrase, borrowed from a speech made more than 60 years ago, has never been less adequate as a description. But because the alternative is to remain forever within the boundaries that biology drew around us, and something in the human mind refuses those boundaries, has always refused them. Refused them when the first hominids crossed a mountain range that every instinct said to avoid. Refused them when the first navigators sailed beyond sight of land into open ocean. Refuses them now, in the 21st century. when the boundary in question is not a mountain or an ocean, but the edge of the atmosphere itself. The cosmos is not hostile to us because it hates us. It is indifferent to us. It does not know we exist. It operates according to physical laws that were established long before life appeared on this planet, and that will continue operating long after the last living thing in the universe has gone dark. The radiation, the vacuum, the cold, none of it is directed at us. None of it is a challenge or a test or a warning. It is simply the universe being the universe. We are the ones who decided to go out into it anyway. That decision, to take a fragile biological body built for a warm, wet, living planet and carry it deliberately into the indifferent hostility of space, is perhaps the most distinctly human act it is possible to perform. Not the technology, not the science, the decision, the willingness, the refusal to accept that the boundaries of the survivable are also the boundaries of the possible. That is what Artemis 3 carries to the moon. In addition to all its instruments and drills and sample containers, it carries that refusal. Wrapped in 300 components and a life support backpack, kept alive by lithium hydroxide and carefully regulated oxygen, standing on the rim of the oldest darkness in the inner solar system, refusing, as our species has always refused, to stay where it is safe. There is a moment in the design of any mission to space when the engineers look at the full list of requirements, everything the mission must accomplish, every environment it must survive, every system that must function without failure. And the room goes quiet. Not the quiet of despair, the quiet of reckoning, the quiet of people who understand exactly what they are being asked to build, and who are beginning to calculate, in the most precise terms possible, the distance between what currently exists and what must exist for the mission to succeed. That moment happened many times during the design of Artemis 3, and what emerged from those moments of reckoning is an architecture so complex, so interdependent, so reliant on the simultaneous success of systems that have never before been operated together in the history of spaceflight, that understanding it fully requires not just technical knowledge, but a particular kind of philosophical patience. The willingness to sit with complexity without reducing it, to hold the whole picture in mind without letting any single piece of it collapse into simplicity. Artemis 3 is not one mission. It is 4 missions conducted simultaneously, whose success is jointly required for any single astronaut to stand on the lunar surface and return alive. The first mission is the launch. The Space Launch System, the SLS, is the most powerful rocket ever brought to operational status. Its Block 1 configuration generates approximately 8.8 million pounds of thrust at liftoff, burning a combination of liquid hydrogen and liquid oxygen in its 4 RS-25 core stage engines. Engines originally designed and flown on the Space Shuttle, rebuilt and upgraded for a rocket whose scale dwarfs anything the shuttle program ever attempted. Augmented by 2 solid rocket boosters derived from shuttle heritage, but stretched and strengthened to contribute the majority of the thrust needed to escape Earth's gravity well. The scale of that number, 8.8 million pounds of thrust, resists intuition. It is more productive to approach it through analogy. The combined thrust of the SLS at liftoff is approximately equivalent to the force required to lift a fully loaded Nimitz-class aircraft carrier. 100,000 tons of steel and aviation fuel and aircraft off the surface of the Earth and accelerated upward. In approximately 8 minutes of burn time, the SLS will accelerate the Orion capsule and its crew from 0 to approximately 25,000 miles per hour. The velocity required to escape Earth's gravitational influence and begin the 3-day transit to the moon. Those 8 minutes represent the most dangerous phase of the entire mission. The energies involved are so extreme, the systems so complex, the margins so precisely calculated, that a failure in any of hundreds of critical components during ascent could be unsurvivable. The launch escape system, a tower of solid rocket motors mounted above the Orion capsule, capable of pulling the crew away from an exploding rocket in a fraction of a second, exists precisely because the designers of this system were honest enough to acknowledge that even with every precaution, the probability of a catastrophic launch failure, while small, is not zero. That honesty is not pessimism. It is engineering integrity, and it is one of the reasons that the abort systems for Artemis are more capable than anything flown on Apollo, because the people who designed them have spent decades studying what can go wrong, and they have designed accordingly. But assume the launch succeeds. Assume the SLS performs flawlessly. The first stage separates cleanly. The Orion capsule and its European service module are injected into a precise translunar trajectory, and the crew begins the 3-day coast to the moon. The second mission begins. The second mission is the rendezvous. Because Artemis 3 does not carry a dedicated lunar lander on the SLS. The architecture chosen for the program, driven by a combination of mass constraints, cost considerations, and the decision to leverage commercial development, places the human landing system on a separate vehicle, launched separately, waiting in lunar orbit for the Orion to arrive. That vehicle is the SpaceX Starship Human Landing System, a variant of the most ambitious rocket ever designed, a vehicle whose full stack stands nearly 120 meters tall and whose Raptor engines, burning supercooled liquid methane and liquid oxygen, represent the highest thrust-to-weight ratio of any engine in operational history. The Starship HLS has been stripped of its heat shield and landing legs, optimized for Earth return, redesigned for the specific requirements of lunar orbit operations, propellant transfer, long-duration loiter capability, the ability to descend from lunar orbit to the surface and return without the benefit of an atmosphere for aerobraking. The rendezvous between Orion and Starship HLS in lunar orbit is a technical ballet of extraordinary precision. 2 vehicles, each the product of different companies, different engineering cultures, different design philosophies, must find each other in the darkness above the moon, moving at velocities measured in thousands of miles per hour, separated by distances that communication signals cross in fractions of a second, guided by navigation systems that must agree on position and velocity to within meters. The docking interface between Orion and Starship HLS represents one of the most critical engineering integration challenges of the program. A physical and electronic handshake between 2 systems that were designed independently and that must perform together flawlessly in an environment where repair is impossible and failure is fatal. This is the architecture that the public rarely sees when they watch mission animations. The animations show the rocket launching, the capsule flying to the moon, the lander descending gracefully to the surface. They do not convey the months of pre-positioned operations required before the crew ever leaves Earth. The separate launch of the Starship HLS, the propellant depot operations needed to fuel it in lunar orbit, the verification that all systems are healthy and ready before the crew is committed to the translunar trajectory, from which there is no easy return. The third mission is the descent. When 2 Artemis astronauts transfer from Orion to the Starship HLS and begin the powered descent to the lunar surface, they are committing to a sequence of events from which there is no abort option during the final minutes. The descent trajectory is calculated to bring the vehicle down to a specific landing zone on the rim of the lunar South Pole, a location chosen for its proximity to the permanently shadowed regions, its access to near-permanent sunlight for solar power generation, and its relatively flat terrain suitable for a vehicle of Starship's dimensions. The final moments of descent represent a navigation challenge of almost incomprehensible difficulty. The vehicle must find its precise landing target in a terrain that is simultaneously more complex and less well-mapped than any landing site previously targeted in human spaceflight history. The lunar South Pole has been imaged by orbital spacecraft, by the Lunar Reconnaissance Orbiter, by India's Chandrayaan missions, by South Korea's Danuri orbiter. But the resolution of those images, while impressive, leaves uncertainties at the meter scale that matter enormously for a vehicle attempting to land on a specific flat area within a landscape of boulders and slopes and crater rims. The Terrain Relative Navigation System on Starship HLS must compare real-time imagery from descent cameras against preloaded terrain maps, identify its position to within meters, and autonomously adjust the descent trajectory in the final seconds before touchdown if the selected landing zone proves unsuitable. This is not science fiction. The technology exists. Similar systems flew on the Mars 2020 Perseverance rover, enabling it to land in Jezero crater with precision that previous Mars landers could not approach, but applying that technology to a vehicle 100 times more massive, descending to a terrain 100 times more critical with human lives depending on the outcome, is a different problem in every dimension that matters. The fourth mission is the surface operation itself, and it is here that the full weight of what Artemis 3 is attempting becomes most apparent. The two astronauts who descend to the lunar South Pole will spend approximately 6 to 8 days on the surface. During that time, they will conduct multiple extravehicular activities, spacewalks in the common vocabulary, though the word feels inadequate for excursions onto an alien world. They will deploy instruments. They will collect samples. They will operate a drill to extract material from the lunar subsurface. They will approach the boundary of the permanently shadowed regions with handheld instruments designed to measure ice content, to map the distribution of volatiles, to read the chemical signatures of material that has been undisturbed for billions of years. Each of those extravehicular activities requires preparation that begins hours before the airlock opens. The suit donning procedure alone takes the better part of an hour and involves systematic verification of every critical seal, every pressure reading, every life support parameter. The pre-breathe protocol, breathing pure oxygen at reduced pressure to purge nitrogen from the blood and prevent decompression sickness when transitioning to the lower pressure of the suit environment, takes additional hours. By the time an Artemis astronaut actually steps outside the vehicle, the infrastructure investment of that single moment stretches back through hours of preparation on the surface, days of transit through space, months of training on Earth, and years of engineering and testing and redesign. Every step on the lunar surface is therefore one of the most expensive single actions in human history, measured in resources, in time, in human effort, in institutional commitment, not expensive in a way that diminishes its value, expensive in a way that amplifies it. Each footprint in the lunar regolith carries the weight of everything that was required to place it there. And yet the astronauts who make those footprints will not be thinking about cost or complexity or institutional history in the moment they are making them. They will be thinking about the next step, about the sample they are about to collect, about the reading on the instrument in their gloved hand, about the terrain ahead and the position of the sun on the horizon, and the status of the life support readings in the corner of their visor display. This is one of the profound paradoxes of human spaceflight. The people who make history are usually too busy surviving to contemplate the history they are making. The perspective, the full weight of the moment, comes later, if it comes at all. It comes in the quiet after the mission, in the years of reflection that follow the intensity of the experience, in the memoirs written and the interviews given, and the moments of private stillness when the reality of what happened finally settles into the body and the mind with its full force. Neil Armstrong described a similar phenomenon after Apollo 11. The landing, the walk, the return. All of it happened in a state of intense operational focus. Every cognitive resource directed at the immediate task, at the checklist, at the problem directly in front of him. The historical enormity of the moment was intellectually understood but emotionally deferred. There was simply no bandwidth for awe in the middle of the mission. Artemis 3 will be no different in that regard. The astronauts who stand on the lunar South Pole, whoever they turn out to be, whatever their personal histories and inner lives, will experience the mission primarily as a sequence of tasks, a cascade of decisions, a sustained exercise in precision and focus and physical endurance. The cosmic significance of what they are doing will wash over them afterward, in the slow time of return and reflection. But we, watching from Earth, have the luxury they do not. We can hold the full picture. We can see the 4 simultaneous missions, the 300 components of the suit, the billions of years of preserved chemistry waiting in the dark below the crater rim, the isotopic signatures of ancient comets frozen in the regolith, the chain of events stretching from the formation of the solar system to this moment. This specific, improbable, extraordinary moment when our species decided to go back to the moon and found something completely different from what it expected. We can feel the weight of it in a way the astronauts themselves cannot, in the middle of the mission, afford to feel. And that weight is real. It is not manufactured by storytelling or amplified by drama. It is the actual weight of the moment. The weight of a civilization reaching the edge of its current capability and deciding, with full knowledge of the cost and the risk and the complexity, to take the next step anyway. That decision was made not once, but thousands of times, by thousands of people, over the years of work that led to this mission. Engineers who chose not to take the easier path when the harder path was more reliable. Scientists who pushed for the South Pole target when the equatorial sites would have been simpler. Astronauts who accepted the radiation exposure, the physical demands, the separation from their families, the probability, small but real and honestly acknowledged, that they might not come back. Every one of those decisions is embedded in the mission architecture. Every compromise and every refusal to compromise. Every lesson learned from failure and every capability built on the foundation of success. The architecture of Artemis 3 is not just an engineering document. It is a record of human choices. The accumulated weight of what a civilization decided mattered enough to attempt. And when the starship HLS finally settles onto the gray regolith of the lunar South Pole, when the dust thrown up by the descent engines drifts slowly back to the surface, in the absence of any atmosphere to keep it suspended, when the first